The speaker is Stanton from University of Southampton in Great Britain, and he's going to talk about loop spaces of Mach associated to flag and low-dimensional simplicial complexes.
Cool. Thank you, Alex, and thank you to the organisers for the opportunity to speak today. So to start off, before I talk about polyhedral products, I'd like to talk about a slightly more general framework of work to do with loop space decompositions. So if we're given a space X, I think we'll all agree one thing we'd like to know about are the homotopy groups of that space. And one way to look at that is by looking at the loop space of that thing, because that just shifts all your homotopy groups down by a dimension. So in particular, ideally, what we might like, and I should say all my spaces are going to be nice path-connected CW complexes. What we might want is if we have a decomposition for the loop space of X as a product of spaces over some indexing set I, of some spaces Y alpha, where each of our spaces Y alpha is an indecomposable space. Meaning that each of these Y alphas up to homotopy aren't some non-trivial product. So in particular, the thing to note is that each of these Y alphas are retracting off a loop space, so each of these Y alphas are going to be an H space. So the first question is we want some list of what the indecomposable factors could be looking like. So the obvious first examples are if you take spheres in dimensions 1, 3, and 7, and this is related to Hopf invariant 1 problems. And also if you look at the loops on a simply connected sphere, M, where M is not 2, 4, or 8. So the homology of each of these guys are torsion-free, but there are also some torsion spaces that were defined, and these were defined by Cohen, Moore, and Eisendorfer. Moore and Eisendorfer defined some spaces which are S, 2 to the M plus 1, P to the R, and these are just the homotopy fiber of the degree P to the R map. And also some T spaces which have a more complicated definition but relate to the EHP sequence, where in this case we have that P is an odd prime and M is greater than or equal to 1. So most of these are indecomposable, and they are certainly H spaces, with a single exception where you take T3P, and this breaks up as a product of another one of these spaces crossed with some other space, U1, which is another indecomposable H space. So with that, so these are just for odd primes. The story the prime 2 is more difficult, but Cohen defines some of these T spaces where you have 2 to the R here, where R is strictly greater than 1. But just for the prime 2, it's a tricky story, and some work has been done by like Paul Seelig and Jelle Gerbich and Ji Wu, and this relates to some unsolved problems in modular representation theory, but I would defer to them to explain any of that. But the point is, just to set up some notation, we're going to define a collection of spaces P bar to be the collection of spaces so I'm going to add in some more spheres in here, but I'll explain that in a second, which will be odd dimensional spheres, loops on even dimensional spheres, these indecomposable T spaces, and also these S spaces, P to the R. So the reason I'm including all of these, because in a minute I'm going to do something called localize, and it turns out if you localize at a prime P that all of these odd dimensional spheres will become H spaces. Oh, don't go that far yet. Yeah, so if you localize at a prime P, at an odd prime, you get a homotopy equivalence which looks like the loop, S2M minus 1 crossed with the loops on S4M minus 1. So you get this homotopy equivalence if you localize at a prime P. So this is just telling you, if you look at the torsion for the odd primes of the even dimensional spheres, that you only actually need to worry about the p torsion in the odd dimensional spheres. But there is a conjecture, which was given by Anik in 92, which is if you let X be a finite, simply connected CW complex, space, so I've said this, CW complexes, then localized, and I'll explain a tiny bit more about this in a minute, at almost all primes, so all but finitely many, P, there is a homotopy equivalence for the loops on X as a product of Y alphas, where each Y alpha is in this collection P bar. So this localization hypothesis, so if you take a space X or some nilpotent space, or we've just got simply connected here in this case, if you localize it at prime P, you get a new space which encodes the P torsion information within the homotopy groups. So what this conjecture is saying, that at almost all primes P, these spaces here should be enough to tell you about the P torsion information within your homotopy groups. And there are a couple of examples, a couple of classical examples. The first of which is the Hilton-Milnor theorem, or just Hilton's version in this case, which is a wedge of simply connected spheres. And this was proved by Hilton, and Milnor generalized it to the decomposition to a wedge of suspensions in 55. And so he decomposed the loop space of a wedge of simply connected spheres as a finite type product of spheres and loops on spheres. And then this result of Cohen, Moore, and Eisendorfer verified this for wedges of Moore spaces, which are kind of a torsion analog of spheres, where they just have a single non-trivial homology group, a reduced homology group, which is Z mod P to the R. And this was proved by Cohen, Moore, and Eisendorfer in 79. And in a slightly different direction, it was also proved for finite rationally elliptic spaces. And this was by McGibbon and Wilkerson in 86. So a rationally elliptic space is just a space where if you look at its rational homotopy, there's only finitely many rational homotopy groups, or it's a finite dimensional Q vector space when you take the direct sum of all of them. And there has been some other work in this direction, for example, for manifolds or Poincare duality complexes, like Beban, Theriot, and Sebastian Chenery have looked at loop spaces of highly connected manifolds and also connected sums of these things. But for this talk, we will be looking at polyhedral products, or in particular moment angle complexes. Yep.
You are assuming the space is finite complex and simply connected. Mm-hmm. So and P can be large.
Yes.
Right?
Yeah.
So why do you need T bracket P to the R and S bracket P to the R as a member of P bar?
Well, so Anik constructed these spaces, these finite simply connected spaces, where the loop space of the homology of the loop space of these things have P torsion for every prime. So in theory, you could need, even if you localize at a large enough prime, you could still need these P to the R spaces in there. Yeah.
Okay, thanks.
There's a question at the back as well. Yes, yeah, he did, yeah. Did Anik show it for 2 codes? Yeah. Right, so let's talk about some moment angle complexes, and I know we've spoken about the homotopy type of these things quite a bit this week, but there are just 2 examples of the homotopy type of these things that I'd like to point out, so I can use them later. And the first one is if you take the moment angle complex of the boundary of a square. This is in fact homeomorphic to an S3 crossed with an S3 in this case. And if you slightly change this by adding in a single vertex into the edge, the homotopy type of this changes quite a lot. And to say in this case is if K is the boundary of an n-gon, for n greater than or equal to 5, I think that's 4, then you get in this case that ZK is diffeomorphic to a connected sum of sphere products with 2 spheres in each product. So this drastically changes the homotopy type, but it would turn out that actually after you loop, you get quite similar decompositions for both of these spaces. So before talking about looping, though, I want to talk a tiny bit more about the homotopy type before you loop. And I will recall what I'm sure is all of our favorite theorem by now, which is the BBCG decomposition, which was proved in 2010, which is where if you look at the suspension of your moment angle complex, this is homotopy equivalent to, oh, there we go, to a wedge over all the missing faces of the 2 plus mod I suspension of your full subcomplexes. So the thing I just want to point out here for later is that the torsion within your moment angle complex is only determined by what's going on in your underlying simplicial complex. And as Stephen spoke about last week, one direction of work is working out for families of simplicial complexes for which this desuspends. And to talk about this, I just want to set up a bit of notation. So we will let W be the collection of spaces homotopy equivalent to a wedge of simply connected spheres. I'll just abbreviate simply connected now, SC, and hopefully not confuse it for simplicial complex, simply connected spheres. And to set up for looking at loop spaces, I'm going to let P be the collection of spaces, H spaces, sorry, which are homotopy equivalent to, sorry, this should be finite type. A finite type product of spheres and loops on spheres. So to look at the first collection, we know that there are many families of simplicial complexes for which we know that our moment angle complex is in W. So I'll just recall a few. So the first one I'll mention is if K is shifted, which was proved by Gerbich and Theriault. In 2007. The second one is if K is a flag complex with chordal 1 skeleton. And this was proved by Gerbich, Panov. No, here I just want the space to be a wedge of spheres. Yeah, because these ones are going to desuspend. And because we have enough suspensions in there, we're going to end up still having a wedge of simply connected spheres. Is that all right? Who asked the question? Or am I looking at... So, oh, sorry. Sorry, I'm... Is that all right? Okay, go ahead. Cool, thank you. Gerbich, Panov, Theriault, and Wu in 2016. And the final one, which generalizes these, is where K is totally homology fillable. published by Irie and Kishimoto in 2018. Right, so the point of looking at this is, no, let me backtrack. So this is the collection where things are a wedge of simply connected spheres, but there are plenty of examples as well where the BBCG decomposition does desuspend, but you don't just necessarily get a wedge of spheres. And this example is if you take K to be the 6-vertex triangulation of RP2, so in the case of a moment angle complex in this same paper here, you get the moment angle complex decomposes as a wedge of some space X, wedge with RP2, where X is some wedge of spheres. Right, where am I? But the point of this, going back to the wedge of spheres, is that if we know that it's a wedge of spheres before you loop, then the Hilton-Milner theorem implies that the loops on ZK is homotopy equivalent to a product of spheres and loops on spheres. But there are plenty of examples where you don't necessarily have a wedge of spheres before you loop, but after you loop, you get a product of spheres and loops on spheres. And one example is one that you can see here, where this isn't a wedge of spheres last time I checked, but after you loop, you get the loops of S3 crossed with the loops on S3. And the first kind of work in this direction was a result of Panov and Terrio. In 2018, which says that if K is flag, I should call it theorem. If K is flag, then the loops on ZK decomposes as a product of spheres and loops on spheres. And I should say here that in this case, the way that they proved it and the way I proved it doesn't give an explicit enumeration of these spheres, but Weilig-Janin did give an enumeration in this case. Gave an explicit, Fedor, Weilig-Janin, yeah. Oh yeah, I should write that. And the first main theorem that we'll talk about is something that I did that generalized this using a very different technique to this. This is a theorem by me last year, is that if we let K be the K skeleton of a flag complex, let's call that L, then the loops on ZK still decomposes in this way. And there are two special cases that I just want to draw our attention to. The first of which is if K is equal to the dimension of L, then this implies that K is flag. So this does indeed recover this previous result that I mentioned. But the other interesting case is the case that K is 1. So you can think of a flag complex just as starting off with any graph and then just gluing in all the simplices that you can. But this implies that you get a decomposition of this form when K is any graph. Right, so the thing to note here is then if you look at the loop space homology of these things, is that this theorem implies in these cases that the loop space homology of ZK is torsion-free. For example, if you take K to be some flag triangulation of RP2 by taking some barycentric subdivisions of the previous one, wherever that's gone, Then from the BBCG decomposition, that we have that the homology of this contains 2 torsion. But after you loop, this torsion goes away. But if you look at this 6-vertex triangulation of RP2, which is here, so we've got 2 torsion in here, but after we loop, if you use like the Hilton-Milner theorem and the James construction, for example, you can show that after looping, this 2 torsion carries on through to your loop space. And this is kind of a thing I'd be interested in if there's some way you can see the torsion from your underlying simplicial complex somewhere within your loop space homology. But I don't have an answer for that at the moment. So these are all examples where after looping, you get a product of spheres and loops on spheres. But in the context of Annick's conjecture, we also had these other spaces, these T spaces and these S spaces. So let's move on to talk about what about torsion. We do have time. So the first result to mention is that Huang and Wu showed that if you look, if X is a finite type H space, if you look at, there is a decomposition for X as a product of Y alphas, where each Y alpha is indecomposable. What did I say? I meant to say P locally, sorry. The P locally, there is a decomposition to Y alphas where each Y alpha is indecomposable. And moreover, this decomposition is unique that you get. And this is true for every prime that you localize at. So with this, I need to find one more collection, and then hopefully that's all, most of my writing done, is that we'll let T be the collection of H spaces, which are homotopy equivalent to the indecomposable factors which appear in this unique decomposition of the loops on a wedge for I equals 1 up to M of some P Ni of some more spaces, P to the I, R to the I, for any M, Ni, Pi, and Ri. So if you vary each of these parameters in here, and you look at all the different indecomposable factors that can appear in here, and you just add all of these to your collection T. So for example, if you take these to be the odd primes, these are these T spaces and these S spaces. But at the prime 2, we know that these factors exist because of this theorem, but we don't necessarily know what they are. We just know that they do exist. And so with this, in the case of a graph, we had that the loop space of these moment angle complexes were in this collection T. So the next natural question to ask is, well, what if we add in some 2 simplices in there? And you can show, which I did, that if you let K be a 2-dimensional simplicial complex, then the loop space of your moment angle complex is in what I'm going to call P union T. So it's a product of spheres, loops on spheres, and possibly some of these spaces as well. So from here, we'll just go through kind of how you would prove this thing. And I'm going to need to set up a couple of lemmas. I'm going to skip one because of time, but which I proved. I'm going to put 23 and 24 because I did it in just the P case first and then extended it to P union T. But this is if you let K be a push out. Let's write this differently. Let K be the union of K1 and K2 over some subcomplex L, where L is a full subcomplex, of K1 and K2. Then, if you know that the loops on your moment angle complex for K1 and the loops on your moment angle complex for K2 are in this collection P union T, and I'm going to put brackets around this because you can just restrict to spaces in P, and then your result will hold just for P, but if you include T, it still holds. Then you get that the loops on ZK is in P union T. And what we're going to do is we're going to kind of iteratively use this theorem to reduce the question of whether your simplicial complex is in P union T down to certain subcomplexes. So with this decomposition of polyhedral products, we also need a decomposition of the simplicial complexes. And this is that there is a push out for a simplicial complex K. Hang on, I need to set up something first. So let's take a vertex V in our vertex set. Then the collection NV is the set of neighbors of V. So these are the set of vertices, this is the subset of the vertex set. So this is a set of vertices which are adjacent to your vertex V. And now I can write the push out, which is that you can write a push out for K as K on the full subcomplex on V union with its neighbors. Down here, you take the full subcomplex without V, and the intersection of both of these is just the full subcomplex on the neighbors. So this probably looks somewhat familiar to the link star restriction push out, but your problem in general with using that, because we want to apply this theorem where we need a full subcomplex here, is that your link may not be a full subcomplex of your simplicial complex. For example, if you take the boundary of a simplex, then your link won't be a full subcomplex. But this is just kind of fattening things up enough to just guarantee that we have a full subcomplex here. So with this, we can state the main result, which we'll use to prove the other two theorems. I need to set up something else again, sorry. Is if we have a simplicial complex K, we'll let CK be the collection of full subcomplexes Ki such that Ki has a complete one skeleton. So every vertex in the one skeleton, every vertex of this is adjacent to every other vertex within your one skeleton. So with this, we can state the result, and this is that that the loops on your moment angle complex for K is in P union T, and I'll put brackets around that again. If and only if the loops on ZKI is in P union T for all Ki within CK. So this would reduce the question down to whether this is in this collection P union T, just to these full subcomplexes which have a complete one skeleton. And we can go through a proof of this. So there's two directions. So the first of which, let's assume that the loops on ZK is in P union T. but there exists a Ki such that the loops on Zki is not in P union T. But we know that this Ki is a full subcomplex, so we know that the loops on Zki next to Denon Masuciu retracts off the loops on Zk, but I proved in this same paper that P union T is actually closed under retract. So this actually just implies that the loops on Zki is in P union T, which is then a contradiction in this case. So for the second case, we're going to do an induction. So we're going to assume that Zki, the loops on Zki, is in P union T for all Ki and Ck. And we're going to do some strong induction. So if in the first case is if K has one vertex, then it's just a disk, so this is contractible, which implies that the loops on Zk is kind of trivially in P union T. So now we'll assume that our simplicial complex is M vertices. So suppose, and that the result's true for all n strictly less than M. And there's two cases that we want to consider in this case. So the first of which is if K is itself in Ck, then just by assumption, we get that the loops on Zk is in P union T. So that one works out nicely. But then the second case is if K is not in Ck, then this implies that there exists a vertex V in our vertex set such that V union with the neighbors of V is not equal to the whole vertex set. So there is a vertex within the one skeleton that it's not adjacent to. So this means in this case we can write K as a pushout, which is K on V union NV, K on the restriction, and we get this pushout like this. And because this is not the whole thing, this is a simplicial complex on strictly less vertices, and this one is just because we've removed V. So this implies by the inductive hypothesis that we get the loops on this full subcomplex and the loops on the restriction is in P union T. And so by the pushout theorem, which is up there, this implies that the loops on Zk is in P union T. Oh yeah, sorry. Okay, I'll do it from now if that's all right. So with this, we can prove the other two cases. I'll probably use that one. Oh, I shouldn't have removed that one probably, but right. So the proof of the other theorems. So the first one was the case where K is the K skeleton of a flag complex. Well, in this case, each of our Ki's within this collection Ck, and these are the only ones we need to consider. So Ki and Ck is the K skeleton of a simplex. And in this case, this means that Ki is shifted, which implies that your moment angle complex is a wedge of spheres. And so we get that the loops on Zki is just a product of spheres and loops on spheres in this case. And therefore, because this is true for each of these in Ck, we get it for K. And then the second case is where K is a two-dimensional simplicial complex. And each of our Ki's and Ck in this case, which Daisuke spoke about, is a one neighborly, meaning it's got complete one skeleton, two-dimensional simplicial complex. So this implies that the BBCG decomposition desuspends. So because we know that, we have a nice decomposition for our moment angle complex. ZKI is homotopy equivalent to a wedge over all the missing faces of a suspension of the geometric realization of each of our full subcomplexes. But now if we look at each of these wedge summons, this is certainly a simply connected, but it's a, say, n minus 1 for some n connected, n plus 1 dimensional complex. So this implies, just by looking at the attaching maps, that there's a homotopy equivalence for this. And this is going to be homotopy equivalent to an X wedge with a Y, where X is some wedge of spheres, and Y is a wedge of Moore spaces. And so what this means is then you have this for each of one of these. So your moment angle complex is just going to be a big wedge of spheres and Moore spaces. I'll try and fit this in here. And this implies that after looping, that you get that this is in the collection P union T. And therefore, this is shown it for all of these, we get the same result for K. So for the last couple of minutes, I'll just mention that, so I've restricted to moment angle complexes here, but there is no reason to. This holds for many other examples of polyhedral products. And these results hold for polyhedral products of the form conon A, associated K in the cases of these theorems, where the suspension of each of your AIs are a wedge of spheres. So for example, you can have generalized moment angle complexes where you have a dn and an Sn minus 1. And you can also show, using this kind of thing, if you're interested in this kind of polyhedral product, it also holds for, say, CPNI, CPMI, for example, where they look the same, M and N, where your MI can be, say, MI is greater or equal to 2, or it can be infinity, and your NI, I guess, is greater or equal to 1. Yeah.
It must be the case that if K belongs to P, then it seems to be the case that if K belongs to your P, then K of J does.
You mean
the wedge construction.
Yeah, I think that should work out. Yeah.
The theorems in the literature are enough to get that.
Yeah, I think so. Yeah. Yeah, and so I'll briefly mention, but I don't have time to talk about it properly. Is you can also use this theorem to give you some localized results. So, for example, you can prove that if each of these KIs are rationally Gollard, if you localize a large enough prime, then you'll get that the loop space of, say, your moment angle complex decomposes a product of spheres and loops on spheres. But I don't have time to go through the details of that, and I'll stop there.